Hello, Geometry International Honor students. Welcome to our 6.4, 6.5 notes video, where we will continue our discussion of special quadrilaterals. Namely, we'll talk about rectangles, rhombi, and squares, which are all special parallelograms. And as you recall, we talked about parallelograms last time. So rectangles, rhombi, and squares are all special types of parallelograms. In fact, as we look at our definition of a rectangle, we define it like this. A parallelogram is a rectangle if and only if it has 4 right angles. All right, so a rectangle is definitely a type of parallelogram, and since it is a parallelogram, that means a rectangle has all the properties that a parallelogram would have. For example, we know that opposite sides are parallel and congruent, okay, true of every parallelogram. Also, opposite angles would be congruent. In addition, consecutive angles are supplementary, and the diagonals bisect each other. So since a rectangle is a parallelogram, then all of these properties that pertain to parallelograms would, of course, pertain to rectangles. Now, in addition, we have a theorem that adds another property to rectangles, and it specifically has to do with the diagonals of a parallelogram. The theorem says the following: the diagonals of a rectangle are congruent. All right? Now, this is a property that is true of rectangles, but not true of all parallelograms, okay? Diagonals are only congruent if the parallelogram is a rectangle. Okay, so let's go ahead and write this theorem in terms of this picture. So in this picture, if we assume that JKLM is a rectangle, if that's our hypothesis, then our conclusion would be the conclusion of this theorem, and that is that the diagonals are congruent. So we'll write it like this. We'll say diagonal JL is congruent to diagonal KM. Now, the converse is also true, okay? So this theorem says if a parallelogram is a rectangle, then its diagonals are congruent. Well, we can turn that around and look at its converse. And the converse says if the diagonals of a parallelogram are congruent, then that parallelogram has to be a rectangle. Okay, so I have a question for you. Imagine you were building a house, and the time had come to cut a hole in the wall because you're ready to install the door. Now, you know that the door is in the shape of a rectangle, okay? So it's really important, if you've ever talked to a carpenter or a builder, they would tell you to measure twice and cut once. You don't want to make a mistake when you're cutting. You want to make sure that this shape that you cut out is exactly in the shape of a rectangle, because that's the shape of your door. So I want you to think of a way that you could guarantee that the opening that you cut in this wall is guaranteed to be the shape of a rectangle. So I'm going to leave that to you if you want to pause the video and think about that right. So I'm going to leave that to you. If you want to pause the video and write your response now, that would be fine. But I am going to ask you next time you're in class, I would like to hear what your thoughts were on this question. All right, so now we're going to move on and talk about our next special parallelogram. We're going to talk about a rhombus. So let's take a look at the definition. A parallelogram is a rhombus if and only if it has 4 congruent sides. All right, so not every parallelogram is a rhombus. To be a rhombus, it has to have 4 congruent sides. Now, since a rhombus is a parallelogram, that means that all the properties that pertain to a parallelogram would pertain to a rhombus. So as you look at this list, Since a rhombus is a parallelogram, that means its opposite sides are parallel and congruent, opposite angles are congruent, consecutive angles are supplementary, and diagonals bisect each other. So all of those things would be true of a rhombus since a rhombus is a parallelogram. Now, in addition to that, we have a couple of theorems that have to do with the diagonals of a rhombus. So let's take a look at those two theorems, and we're actually going to prove them. The first one says if a parallelogram is a rhombus, then its diagonals are perpendicular. All right, so let's prove that. So our hypothesis is that we're assuming we have a rhombus. So our given statement would be that we have rhombus ABCD. ABCD. All right, and what we're going to prove is we're going to prove that the diagonals are perpendicular to each other. Or in terms of this diagram, we're going to prove that segment AC is perpendicular to segment BD. All right, so the way that we're going to do that is we're going to prove a couple of triangles congruent. We're going to prove that this yellow triangle, triangle ABE, is congruent to this green triangle. And then once we have done that, then we'll be able to say that angle 1, whoops, that's not what I meant to do. Hold on. We'll be able to say that angle 1 is congruent to angle 2. Now, if you look at angles 1 and 2, they are a linear pair of angles. And you might recall from last semester, we proved a theorem that says the following. If we have a linear pair of congruent angles, then they had to have been formed by perpendicular lines. So let's get angles 1 and 2 congruent to each other by proving that the yellow and the green triangles are congruent. So we'll start with the fact that we are assuming that we have a rhombus. So we have rhombus ABCD. Okay, the justification for that is that it's given. That's what we're assuming to be true. All right, well, since it's a rhombus, that means that we have segment AB congruent to segment BC. Let's mark that. AB is congruent to BC. All right, and the reason why that is true is because it's a rhombus. So we'll back that up with the definition of a rhombus. A parallelogram is a rhombus if and only if it has four congruent sides. All right, now if you look at the two triangles, they share a side. They share a side BE. So we're going to say that segment BE is congruent to itself. And the reason is reflexive property of congruence. All right, and then also, since this rhombus is a parallelogram, we know that diagonals bisect each other. So this diagonal AC is being bisected. Okay, so we have the side that the two triangles share. Okay, and then now we're going to be able to say that this side is congruent to this side because it's a diagonal of a rhombus that's being bisected. So we'll say in step 4, we're going to say that segment AE is congruent to segment CE. And the reason is because if a shape is a parallelogram, then its diagonals bisect, and I'm just going to abbreviate E period, O period for each other. All right, so if we were keeping track, we would see that we have 1, 2, 3 pairs of congruent sides. So that's enough to conclude that the two triangles are congruent. So we're going to say triangle ABE is congruent to triangle CBE. And the reason is because side, side, side implies congruent triangles. Okay, once those triangles are congruent, then we can say that angle 1 is congruent to angle 2 by CPCTC. Okay, so then again, let's look at our diagram. 1 and 2 would be a linear pair of congruent angles, so that means they had to have been formed by perpendicular lines. So our last step will be to say, in step 7, we can say that segment AC is perpendicular to segment BD, and the reason is because a linear pair of congruent angles implies perpendicular lines. All right, so that's our first theorem about the diagonals of a rhombus. We have just proved that if a parallelogram is a rhombus, then its diagonals are perpendicular. Now what we're going to prove is that if a parallelogram is a rhombus, each diagonal bisects a pair of opposite angles. So to do that, we're again going to use congruent triangles. What we're going to do is we're going to prove just basically half of this theorem. We're going to prove it true for this diagonal RP. We're going to prove that angles 1 and 2 are congruent to each other, and that angles 3 and 4 are congruent to each other. Now, a similar proof would be to show the same thing about diagonal NQ. So we're not going to write a proof about both diagonals. We'll just prove the one diagonal, and then the proof of the second diagonal would be similar to that. All right, so what we're going to do is we're going to do this again by using congruent triangles. So what we'll do is we will prove that this yellow triangle RNP, is congruent to the green triangle. And once we get those two triangles congruent, then angles 1 and 2 will be congruent by CP/CTC, and angles 3 and 4 will be congruent for the same reason. So let's go ahead and assume that we have a rhombus. So our given statement is that we have rhombus NPQR. And what we're going to prove is that angle 1 is congruent to angle 2, and then angle 3 is congruent to angle 4. So let's get busy and get those two triangles congruent to each other. So we'll start with the fact that we have a rhombus NPQR. Okay, and that was given to us. All right. And since we have a rhombus, then that means we have some congruent sides. We can say that NP is congruent to PQ. Let's go ahead and mark that. NP is congruent to PQ. And also we have segment RN congruent to segment RQ. Okay, RN congruent to RQ. Okay, and the reason why is because we were assuming that this shape is a rhombus. So we can back that up with the definition of rhombus. All right, then in step 3, notice that the two triangles also share a side. All right, the segment RP is congruent to itself. So let's go ahead in step 3 and say that RP is congruent to RP. And the reason is because of the reflexive property of congruence. All right. And then step 4. Let's kind of keep track here. We have 1, 2, 3 pairs of sides congruent. So that's enough to conclude that we have congruent triangles. So we can say that triangle RNP, that is the yellow one, is congruent to triangle RQP, the green one. And the reason why is because side, side, side implies congruent triangles. All right, now that we have the triangles congruent, we can say that angle 1 is congruent to angle 2, and that angle 3 is congruent to angle 4. And the reason is because corresponding parts of congruent triangles are congruent. All right, so what we have proven is that we have one diagonal that bisects a pair of opposite angles. Now, we could write a second proof, but it would be very similar. We could prove the same thing about NQ. We could get a couple of triangles congruent, and then because of CP/CTC, angle 5 would be congruent to angle 6, and angle 7 would be congruent to angle 8. So now let's work a couple of examples that have to do with the diagonals of a rhombus. So in this example, the diagonals of rhombus FGHJ intersect at K. Use the given information to find each measure or value. So in letter A, if we have measure the measure of angle FJH is 82. So let's go ahead and mark that. So this angle that I'm going to mark with the red arc is an 82-degree angle. we're being asked to find the measure of angle, let's see, KHJ, which is this one. So I'm going to mark it with a black arc. So that's what we are being asked to find. And so let's use what we know about the diagonals of a rhombus. Well, first we know that the diagonals of a rhombus bisect opposite angles. So this red angle is being cut into two congruent angles. So I'm going to mark half of one with a blue arc, and we'll write down that that blue arc, or that angle with a blue arc, has a measure of 41 degrees, okay? We also know that we just proved a minute ago that the diagonals of a rhombus are perpendicular to each other. So let's put a right angle right here, which makes this little triangle a right triangle, okay? So what do we know about the acute angles of a right triangle? They are complementary to each other. So if this blue angle is a 41-degree angle, that means that this angle with the black arc would be its complement, or in other words, a 49-degree angle. So the answer to our question is that the measure of angle KHJ is equal to 49 degrees. All right, and then letter B, it says if GH is x plus 9 and JH is 5x minus 2, let's find x. Well, GH and JH, okay, are sides of a rhombus. And what makes a rhombus a rhombus? The fact that the sides are congruent. So if GH is, let's see, x plus 9, and JH is 5x minus 2, since those are sides of a rhombus, we know that those sides are congruent to each other, therefore the measures are equal. So let's write an equation that says x plus 9 is equal to 5x minus 2, and then we'll solve that for x. I'm going to subtract an x from both sides, and then add 2 to both sides, all right? And lastly, divide both sides by 4. So x is equal to 11/4, or we could call that 2.25. All right, so that leads us to our last special parallelogram, and that's a square. Here's our definition of a square. A parallelogram is a square if and only if it has 4 congruent sides and 4 congruent angles. In other words, what makes a square a square? The fact that it is both a rectangle, a rhombus and a rectangle at the same time. Okay, so let's go ahead and use this Venn diagram to kind of summarize all this talk we've had about parallelograms. So I'm going to let this outer shape represent the set of all parallelograms. So let's go ahead and label this as the set of parallelograms. And remember, what makes a parallelogram? The fact that it has 2 pairs of parallel sides. All right? Now, there are some special parallelograms. The first one we talked about was rectangles. Now, you'll notice that this rectangle oval is completely contained in the parallelogram shape because every rectangle is a parallelogram. So rectangles, as you recall, are parallelograms that have 4 right angles, okay? Another special rectangle was a rhombus, okay? So I'm going to write rhombi. By the way, rhombi is plural for rhombus. So 1 rhombus, 2 or more rhombi. Now, what makes a rhombus a rhombus? The fact that it's a parallelogram that has 4 congruent sides. So again, notice that this rhombi oval is completely contained in the parallelogram shape because every rhombus is a parallelogram. All right, so then let's talk about this intersection right here. The intersection of the set of rectangles and the set of rhombi. Well, if a parallelogram is both a rectangle and a rhombus at the same time, then that means it is a square. All right, so that kind of summarizes all the different special parallelograms we've talked about. So now let's do this. Let's take a look at conditions that guarantee that a quadrilateral is a rhombus or a square. Okay, so number 1, if we have a parallelogram with perpendicular diagonals, okay, that's enough to conclude that that parallelogram has to be a rhombus. So that is a condition of a parallelogram that guarantees that it has to be a rhombus. So let's go ahead and write this, write that condition in terms of this diagram. So this is a parallelogram. So let's go ahead and assume that, let's assume that JKLM, JKLM is a parallelogram, and let's assume that it has perpendicular diagonals. So we're also going to assume that KM is perpendicular to JL. Then we can conclude that that parallelogram JKLM has to be a rhombus. Okay? Condition number 2 says if one diagonal of a parallelogram bisects a pair of opposite angles, then that guarantees that that parallelogram has to be a rhombus. All right? So let's write that in terms of this diagram. So we're going to assume that WXYZ is a parallelogram, and we're going to assume that angle 1 is congruent to angle 2, and angle 3 is congruent to angle 4. So we have a parallelogram with one diagonal that bisects a pair of opposite angles. Then that guarantees that that parallelogram has to be a rhombus. Okay? Number 3 says if a parallelogram with one, or if we have a parallelogram that has one pair of congruent consecutive sides, okay, we don't need to worry about the other pair of sides. That's enough to guarantee that that parallelogram has to be a rhombus. All right, so let's write that in terms of this diagram. So if ABCD is a parallelogram and side AB is congruent to side BC, in other words, we have a pair of consecutive congruent sides, then we can conclude that that parallelogram has to be a rhombus. Okay? And then last but not least, and as we saw above in the Venn diagram, if we have a quadrilateral that is both a rhombus, or excuse me, both a rectangle and a rhombus, then we may conclude that that quadrilateral is a square. All right, so now what we're going to do is we're actually flipping this lesson, so you've done the lesson at home. We'll do the homework when you get in class. So I will assign that when I see you in class next time. And if you have any questions about this lesson, make sure you write them down so you can be sure and ask me.